In this section of the class, we're going to begin talking about some of the applications of integrals to some very common physics problems. And so in this video, let's talk about the application of integrals to finding the mass of an object whose density may be varying along its length. Now let's recall the relationship between density and the total mass of an object. Density is a representation of how the mass of an object is distributed along its length. If an object is very, very dense at a certain point, it will have a lot of mass contained in a very small volume, in a very small spatial area. So, if you have a one-dimensional object of length L, and along the entire object, the density is a constant value. Let's call it the Greek letter rho. Then how can you find the mass of the object? You can take the length of the object and multiply it by the density. If you have a constant density, the mass is just density times length. Very simple calculation. But what if your object has a density that is not constant? Maybe it's denser at one point than it is at another point. If you have a density function for your one-dimensional object, at position x, the density is rho of x, you can still find the mass of the object between any point along the object and any final other point on the object. You can find it by integrating the density function, rho of x, with respect to x, from the initial position to the final position. So let us go ahead and apply that formula to the following exercise. I think I used delta for the density here. Let's just make that rho for consistency's sake. Suppose that the density of an object is given by rho of x equals x minus 1 squared plus 1 at position x. One end of the object is located at the coordinate x equals 0 and the other at x equals 2. So what's the object's mass? And to find that, we can simply integrate from the initial position to the other end of the object this density function, x minus 1 squared plus 2 with respect to x. Now, this can be integrated relatively simply using a u substitution of u equals x minus 1, so that du is equal to dx, directly speaking. Then, when x is equal to 0, u will be equal to negative 1, and when x is equal to 2, u will be equal to positive 1. So we can integrate from u equals negative 1 to positive 1, u squared plus 2 du, giving us u cubed over 3 plus 2u, evaluated from negative 1 to 1. Then, plugging in these two numbers, we have a final answer of plug in 1 cubed over 3 plus 2 times 1, take away negative 1 cubed over 3 plus 2 times negative 1. It is of course also possible to find the antiderivative of your integrand using not u substitution, but by just multiplying out this x minus 1 quantity squared. This is just a nice change of pace that I was in the mood to do today. So this number, when you simplify it, will give you the total mass of this object based on its variable density function.